Welcome back. For this lecture, we're going to finish off our discussion of asymptotic notation. We're going to use or learn about some techniques for solving these types of problems that are way easier than using the definitions. You've listened to me prove stuff from the definitions for a long time. You've earned this. Using these facts better resembles how you use asymptotic notation in the real world. It's not quite the same, but it's getting there. And on assignments and quizzes and the final exam, you should pay attention to what it says you're allowed to use. If it says to prove something like this from the definition, use the definition. You still have to remember it. But if it says like from the given facts or something, you could do what we're about to do today. All these facts are posted in this week's readings. So for the first example, we're going to show that n plus 1 is in little o of n squared. So this linear function grows a lot more slowly than this quadratic function. When you do questions like these yourself, it's going to be a bit of a scavenger hunt. But luckily for this lecture, we know what facts we're going to use ahead of time. And I'm just going to explain why each one applies. So we start by using fact 1.3. If a is less than b, then n to the power of a is in little o of n to the b. From that, we know that n, which is n to the 1, is in little o of n squared. So this works in general. N squared is in little o of n3. N to the 5 is in little o of n to the 10. And also it works for fractional powers. So n to the power of 1/2, that is square root of n, is in little o of n. Then by 1.1, we use a similar rule for constants. Any constant function is in little o of any logarithmic function, as long as the base is greater than 1. And then by 1.2, we move a bit higher up the hierarchy. Any logarithmic function, regardless of the base, is in little o of any polynomial. And then by transitivity, we know that 1 is in little o of log 2 of n, and log 2 is in little o of n squared. And because of that, we're able to say that as a result, 1 is in little o of n squared. This is just like how chains of inequalities work with numbers. These two assumptions are basically saying x is less than y and y is less than z. And then from that, you can conclude that y is less than z. Same thing with these functions and little o. Next, we use the sum rule that we talked about last class. Maybe not the exact same one, but one very similar. I'm not sure if we talked about little o or big O or whatever. We know that n is in little o of n squared and that 1 is in little o of n squared. From that, we know that n plus 1 is in little o of n squared. Wasn't that so much nicer than a definition? I don't think we had to look at a single inequality. And so we keep moving. Now we're going to show that n cubed is in big O of n cubed plus 1. So basically, n cubed grows about the same rate or slower than n cubed plus 1. We sort of reduce this into a different question, I guess. 3.2 tells us that if n cubed plus 1 is in big omega of n cubed, then n cubed is in big O of n cubed plus 1. That way, you can do a slightly easier proof of showing that n cubed plus 1 is in big omega of n cubed, and then that will imply the result we originally want. And just like how that transitivity rule had an analog for regular inequalities with numbers, being able to reverse big O and big omega like that is just like how you're able to flip inequality around. Fact 5.1 says that any constant multiple of another function is in big omega of the original function. Intuitively, that makes sense. We've sort of learned to not worry about constant multiples. It's the operations on n that matter. So if you multiply a function by a constant, its asymptotic growth rate will sort of be in the same class as it was before. In this case, we use a constant c equals 1. N cubed is in big omega of itself. It's easy. And then we use the rule that f is in big omega of g if and only if f is in both big theta of g if and only if f is in big O and big omega. The analog for numbers is that if you have both x is less than or equal to y and x is greater than or equal to y, the ranges of values that the numbers can take on sort of just smushes together to make x equal to y. Same thing with these less than or equal to and greater than or equal to analogs and the analog to being equal. So because n cubed is in big theta of itself, we're able to conclude that it's in big omega of itself. It's equal to itself, so it's greater than or equal to itself. And then we use a similar sum rule from last time. We know that 1 is in n cubed. I guess that's not really justified in this example. I don't really like that. For full marks, I would rather have you specify that 1 is in this case, big omega of n cubed. Wait. What's g? Wait, this is messed up. Because 1 isn't in big omega of n cubed. It's much smaller than n cubed. I think that if g is a constant, then the rule works. It's not very well explained here either. This example's a bit of a dud. Now we're going to show that n cubed is not in big theta, n squared is not in big theta of n cubed, so they're not of equal growth rates. We use the rule that we used earlier, that any polynomial is in little o of a bigger polynomial. And then we use a new rule. If f is in little o of g, then it's not in big omega of g. This is just like how if x is strictly less than y, then we know that it's not equal to y and it's not greater than y. So then we're able to say that it's not greater than or equal to y. Likewise, we know that n squared grows way slower than n cubed, so it doesn't grow faster and it doesn't grow at the same rate. That equality thing comes up again. We know that n squared is in big theta of n cubed if and only if it's in both big O and big omega of n cubed. But we just found out that n squared is not in big omega of n cubed. Just like saying we know it's x is equal to y if x is less than or equal to y and greater than or equal to y, but we just found that it's not greater than or equal to y. One side of the AND statement is false, and thus the entire AND statement is false. And we conclude n squared is not in big omega of n cubed. Now we have n log base 3 of n, and we see that that's in little o of n cubed. We use the hierarchy summarized again. Any logarithmic function is in little o of any polynomial. In this case, log base 3 is in little o of n to the power of 1. Additionally, every polynomial is in little o of every bigger polynomial. In this case, n is in little o of n squared. So by transitivity? Not necessarily. Oh, okay. This is like the asymptotic version of that inequality implication that tripped up a few of us earlier. Remember that for any OR statement, only one side of it needs to be true for the whole thing to be true. In this case, if x is less than y, then we can conclude that it's less than or equal to y because x less than or equal to y just means x is less than y or x is equal to y. It works similarly for asymptotic notation. N grows way smaller or way more slowly than n squared. Therefore, n grows way more slowly or at the same rate as n squared. It doesn't grow at the same rate, but it's still true that it grows way more slowly or at the same rate. We combine the things we found so far along with fact 5.4. This is sort of a product rule for functions. We can multiply something that we know is in little o of n with something that we know is in big O of n squared to get something that, by this fact, we know is in little o of n cubed. The first step of this uses another aspect of the hierarchy. Any polynomial is in little o of any exponential function. We use a constant multiple rule to show that 2 to the n is in big omega of itself. I guess this is a generalization of the fact that every function is in big theta of itself, and any constant multiple of a function is in big theta of itself. I guess it's more elegant to put them into one rule if they use the same underlying principle. Then, since we have big theta, we can conclude big O. 2 to the n grows at the same rate as itself, so we can say that it's the same rate or slower than itself. And we use that product rule. We have 2 functions, one of which is in little o of 2 to the n, the other is in big O of 2 to the n. And their product is in little o of 2 to the n times 2 to the n, which is 4 to the n. N squared plus 1 is in big theta of n squared. We use that theorem about the relationship between big theta, big O, and big omega again. We don't really have an easy way to prove that something is in big omega using these facts, and we're all tired and burnt out and stuff, and we don't want to use the definition. So we can reduce this to an easier problem. Instead of showing that it's in big theta, we're going to separately show that it's in big O and big omega. 5.1 again, constant multiples. Every function is in big theta itself because it grows at the same rate as itself. N squared is in big theta of n squared. Then you use that fact again to say that n squared is in big O of itself and in big omega of itself. Oh, great, it's that one that I didn't, or that I got a bit confused about. If any of you are confused about this after it's had time to sink in, let me know. This is probably just a skill issue on my part that I'm getting confused about it, but it might actually be written in an unclear way. If it is, I'll investigate and fix it. But for now, I think that there's just some inconsistent notation. G is a function here, but unspecified here, and I'm pretty sure G is meant to be a constant here. Which lets us say that we know that n squared is in big omega of itself, and thus n squared plus 1 is in big omega of n squared. And also intuitively it makes sense. N squared plus a little bit will always be slightly greater than n squared. So then if you bring constant multiples into it, they'll have the same asymptotic growth rate. Cool. Then we've shown that n squared plus 1 is in big omega of n squared. Showing that it's in big O will take slightly more work. We aren't able to immediately guarantee that adding a constant will keep it slower than or the same rate as the other one. But we can just use the hierarchy. A constant grows more slowly than a logarithm because it doesn't grow at all. And a logarithm grows more slowly than a polynomial. And by transitivity, we can conclude that a constant grows slower than a polynomial. And then the whole less than implies less than or equal to thing. A constant grows slower than a polynomial, so it grows at the same rate or slower as a polynomial. We found that n squared and 1 are in big O of n squared. So by our sum rule, n squared plus 1 is in big O of n squared. So as you can see, this lets us mow through some specific examples of functions pretty quickly and hopefully pretty easily. We can also show these or use these to show general facts about asymptotic notation. So let f, g, and h be arbitrary functions from the positive integers to the positive reals. First, we're going to show that if f is in big theta of g, then g is in big theta of f. With general statements like these, it's good to use what you already know about numbers and inequalities to wrap your head around what you're learning about the corresponding concepts for functions and asymptotic growth comparisons. In this case, say you have two numbers, x and y. If x is equal to y, then y is equal to x. That's what's going on here. So we start by assuming that f is in big theta of g. Because of that good old inequality rule, we now know that f is in big O of g and in big omega of g. And then we can do the thing that's equivalent to reversing the inequalities. We started with x equals y, and we can tell now that x is less than or equal to y, which implies that y is equal to x. Same story with how x is greater than or equal to y, and thus y is greater than or equal to x. Or y is less than or equal to x. It reverses. But what we just stumbled on is 3.1. G is in big omega of f, and g is in big O of f. If and only if means that it works both ways. So we can conclude that g is in big theta of f. Now we'll show that if f is in big omega of 1, so f just has any growth rate at all, then f plus some constant is in big theta of itself. So we let c be a positive constant and suppose that f is in big omega of 1. That equality rule keeps popping up. And in this case, since we're trying to see that f plus c equals or is in big theta of f, we can just show that it's in big O and big omega of f. We use that again to show that f is in big theta or big omega of itself, and use that weird rule to say that f plus some constant is in big omega of itself. This should remind you of an example we did earlier. We are able to use the weird rule to say that think it was n squared plus 1 is in big omega of n squared. And then we just had to do slightly more work to show that n squared plus 1 is in big O of n squared. We do the same here. F is in big O of itself because it's in big omega of itself. Oh, silly me. We don't actually need to mess with the hierarchy. We already assumed that F is in big omega of itself, or F is in big omega of 1, so we can just do the inequality reversing thing. 1 is in big O of F. Then we're using the sum rule, right? Yeah, a constant exhibits constant growth, so it's, a constant exhibits the same growth rate as a constant, so it's in big theta of 1. Inequality rule says that C is in big O of 1. And then the sum rule, no, transitivity, dang it. I think my incorrect predictions here should illustrate how there are multiple ways to solve each problem. It's not a universal truth that to prove this you have to use 5.1 and then 3.1 and then 3.2. This is one correct solution among many. Anyway, 2.1 with the conclusion of 4, transitivity. We know that 1 is in O of F and C is in O of 1, so C, O of 1, O of F. C is in big O of F. Wow, now we get to use the sum rule. We know that F is in O of F and C is in O of F, so F plus C is in O of F. So we just found that it's in big O of F here, and we found that it's in big omega of F here. So we can conclude that F plus C is in big theta of F. And we're in Saskatchewan. We're done. Phew. There will be practice questions about asymptotic notation posted later today, I think, hopefully. Don't even look at them right now. Focus on the assignment. But later on, I strongly recommend both proving them from the definition and using the facts we learned today. Next week, we're going to go deeper into computer science. Have a good weekend and good luck on the assignment.